ones you can certainly do on your calculator. I wouldn't recommend it, but it can be done. In fact, let me see if I can get my calculator. If we wanted to do some of these the hard way, and it would be also easy, if we wanted to calculate the log base pi of the square root of pi, the hard way would be to say, well, I'm going to need the change of base formula to do it on my calculator. And so this would be, for example, the log of the square root of pi over the log of pi. In our calculator, we could do that. We would type in, let's see, the log of the square root of pi, so log square root pi, close the square root, close the log, divided by the log of pi. And we see we get 0.5. It's a fairly interestingly clean answer. And the idea behind this is that if we see it as the log base pi of pi to the 1/2, again, square root 1/2 power, then that should equal 1/2 directly by the identity that log base a of a to the x equals x, and a raised to the log base a of x also equals x. These are cases of a function composed with its inverse. That is, in general, f of f inverse of x should equal x, and f inverse of f of x should also equal x. Okay? And we're just using this property right here. Now the second one, you can do in your calculator, and it's a little pain in the butt to do, and if you wanted to do it in your calculator, it would be change of base, so you would be doing something like this. 3 to the log base 3 of pi equals 3 raised to the, well, we can go to say base 10, or let's go to base e this time, do a little different. So we'd have ln of pi over ln of 3. And our calculator, we can do that. Let's see what we get. We get 3 raised to the parentheses ln pi divided by ln 3. Close my exponent. And I get this strange number. Well, it's only strange if you don't recognize that this number is the calculator's approximation for pi. And so we get pi out of this. And you could check, but again, this 3 raised to the log base 3 of pi is in fact exactly the use of this identity. And so the answer here should be pi. Now the next one is the asymptote of 2 to the x plus 3. Well, again, we could start with the idea of what does the graph of 2 to the x look like. And if we still have it, yes we do, generically, we have, this is what the graph of 2 to the x would look like, and 3 to the x and e to the x. In fact, all the a to the x's will look similar to this. They'll be increasing, same domain range, same asymptotes, same y-intercept, as long as a is greater than 1. And again, if a is between 0 and 1, you'll get a different graph. Remember, the two legitimate bases are between 0 and 1 and from 1 to infinity. So what we have is the graph of 2 to the x plus 3. And if you remember from transformations, that what we start with, for example, this might be the graph of 2 to the x. That would be 2 to the x. And if we add 3 to it, it's going to go up 3 units. So my scale might be a little funny, but in any case, what was the x-axis is now at 3. And what was at 0, 1 is now at 1, 2, 3, 4. So the y-intercept has moved up here. So we get a graph that looks something like that. Okay? It's been shifted up by 3. And we see what was the horizontal asymptote for y equals 2 to the x is up here now. This is a horizontal asymptote for y equals 2 to the x plus 3. So it's a horizontal asymptote. It's a horizontal line whose equation generically is y equals a number. In this case, it would be y equals 3. And we have some questions now about 0.4 to the x. What is its inverse, and is it increasing or decreasing or neither? Okay, so again, generically it's nice to have maybe a picture in your head of what an exponential function looks like whose base is between 0 and 1. It looks like this. This would be a graph, for example, of f of x equal a to the x for a in the interval 0, 1. That's the interval 0, 1, not the point. Okay. And of course it has an inverse. It's decreasing, so we can certainly choose decreasing for this. And its inverse, well, the inverse would be the reflection across this line y equals x. And that would be the graph 0, 1 goes to 1, 0. And the inverse would be the logarithm not the world's prettiest picture. Okay, not the greatest reflection, but good enough. They should actually cross at this point on y equals x, but in any case, f inverse of x will be the log base a of x. And you see this one is decreasing, a to the x is decreasing, and log base a of x is decreasing. Okay, and so we have this would be log base 0.4 of x. Okay. And this last one asks us to simply match some of these. Okay, and remember our properties. And this first one we know should equal ln of 2 plus ln of x. And this one will equal ln of x minus ln of 2. And we'll check to see. Those are the easiest ones. So let's see. We see ln of x plus ln of 2 right there. So that's 4. And ln of x minus ln of 2 is 5. And this one is 2 ln of x. And that would be 12. And this last one would be x ln 2, which would be 11. This one doesn't simplify. So the answer in this case would be none. That is, the logarithm of a sum does not simplify. It doesn't mean any sum doesn't simplify, just a simple sum like this. For example, you might wonder about ln of, well, x plus x, for example. That's a simple case in which we get ln of 2x, which would be our first one. That one does simplify, but not directly from a sum. Or you might have something like ln of x squared minus 4, which is not technically a sum. It's a difference, but the same idea holds. And we can write this as x minus 2 times x plus 2. Now what was a sum or difference becomes a product, and we can expand. I don't know if that counts as simplifying, but certainly we can expand it. But in general, you can't do anything with these sums like this one here. And that would be key.